produce it hard enough to remove those adverse fluids. We've got to produce it gently enough so that we don't hurt the frac jobs and the natural fractures. So, yeah, exactly. The ridiculous limit is not at all, but that obviously isn't right either. So the key to it, and this is part of why this is such an important discussion, this is a way to engage what rate is right. That said, I've had the privilege, I'm going to get to have, it is very unusual to get to present twice at one of these advanced technology workshops. And they've invited me to do 2 different presentations at the same one, which scares the daylights out of me. Not sure I've got that much useful to say. What I have seen and what I'm going to be telling them, it's not about the rate. It's about the pressure. If you handle the pressures correctly, and obviously you say, well, gosh, it's rate. Yeah, because delta P implies rate. If you don't put enough drawdown, if the rate isn't high enough, if you don't put enough drawdown on it, you don't clean up the well, and you damage it that way. If you put too much drawdown on it, you damage it the other way. Both are permanent. They are not, once they happen, you're toast. You've got to go do a new frac job or acid job. But it is conceivable, and this is the way to evaluate that. It is very likely that if you don't produce it hard enough, you'll hurt it. If you produce it too hard, you'll hurt it. So both extremes. I mean, basically, if you thought about it, it's kind of a bell-shaped curve. This stuff over here is bad. This stuff over here is bad. Someplace in the middle, your task is to find that sweet spot. Early time. Rarely see stories. We beat up that. Often see fractured wells on the E1 discussion we had. Aggressive flowback will harm the well. The better wells occur when time to maximum productivity is minimized, which goes right to the heart of your question. To find the right rate to minimize the amount of time it takes to get the best performance. And the program, because it's based on looking at the real data, permits you to see virtually any kind of data set. The hourly, day by the second, whatever. Right? So that's the early time stuff. Let's run quickly with the middle time, and then let's go look at some real data. Ryan, have you checked the road conditions?
Yeah, sort of. They're okay. Not great.
Middle time. This is not a story about the Hobbit. Okay? You may think I look like a hobbit, but I'm about twice too tall. And by the way, my feet are not webbed, and I don't have pointy ears. So I no way. Okay, never mind. I'm not yet. Okay. Middle time, not middle earth. Middle time. When is middle time? Middle time is after a dimensionless time of 1, but prior to the onset of a real pseudo-steady state. The shape of the flow pattern, and notice I did not say circular or radial. That flow pattern is not circular or radial. It is ovoidal. O-V-O-I-D-A-L. Ovoidal. It is the shape of an A. All right? Because it's probably going this way here, and a little bit there, and a whole lot over there. And it is such a wrong picture to have this middle picture of the pressure wave looking like a pipe. That just doesn't happen. So to think about this flow pattern as the shape of an A at least begins to engage this idea of the elliptical character of the flow pattern. The wellbore and the near wellbore fractures are now in equilibrium. It's a crude analogy, but I think it's an appropriate way to think about it. At that stage in the life of the wellbore and the near wellbore fractures are in pseudo-steady state. They are, in effect, boundary dominated. The pressure wave has found the boundary, aka the perforations, in the wellbore, and it has found the extent of the natural fracture system. All right? So in that setting, that part of the system is in equilibrium or arguably in pseudo-steady state. But no boundaries have been encountered. So we haven't seen, really important question. Well, what's a boundary? Well, boundaries can be as simple as a clay drape. I hope that you all get to do a summer field camp and go out and crawl around a few rocks. Because in spite of the fact that we get all frustrated with the geologists, our job is all about geology. Everything we do is contingent on understanding the geology of the system. So the things that create boundaries can be nothing more than a simple little 1/8 of an inch thick clay drape that's enough to not allow the pressure drop to go across it. It might be a fracture that is liquid filled that serves as a pressure boundary. Okay? I mean, goofy stuff. You stop and think about it a minute. Okay, I drilled a well into this block of rock surrounded by a natural fracture system. That natural fracture system has water in it. I've got to have enough pressure drop across that water boundary to cause flow to occur through that. That becomes a boundary. It's a boundary as real as if it were a solid sheet of steel. Okay? So the things that become boundaries sometimes are amazingly unusual. Before interference or other sources have begun to influence the well, while the log-of-time plot gives a straight line for radial anisotropic systems. Okay? So that's basically what we're going to. So we're looking at the behavior out here after log of time at 1. Okay, so we're looking at the stuff to the east, but prior to it going up on these unit slope lines. We're looking for this more or less linear signature. That's what we seek to find on the RPI versus log of time or square root of time plot. All right? We can expect to see changing transmissibilities, both harmful and beneficial. The slope steepening or the slope shallower. Some of the reasons why it would get shallower. This specific piece right here is a piece of work that Cosme did in Yates Field in Texas. Transition. Basically the change in the mobility in the phase. The same idea as I pushed on you a minute ago about storage. Additional zones contributing. The thickness of the system changes. Right? I've got the drawdown enough that the new zone below me started to produce as well. All right, so one of the things that you will see, I'm very confident you will see it if you decide to start really digging into production analysis. You will see the slope of the line change. Sometimes it gets shallower, sometimes it gets steeper. The change in steepness, I have become convinced that the change in steepness predicts both where and how severe. If it's really close to the wellbore, that is to say the natural fracture volume is relatively small, I can imagine this event to be a very sharp, sudden change. Sometimes you see that. Sometimes it literally takes months to make that transition. Very slow. And I think that's telling you something about the geometry of the system. It's telling you about how much transition there is. Because, you know, you think about the geology of a naturally fractured system, it's pretty easy to understand that some natural fractures would have a very sharp contrast. They're all about the same size, so they all have about the same conductivity. So when the pressure wave gets done moving through those, bam, that piece is over with, and now you're into the matrix-dominated response, a sharp event. On the other hand, I could also imagine that in some reservoir systems, you've got some really big natural fractures transitioning down through all different sizes, down to literally nanoscopic fractures. So you've got this wide range of fracture sizes, and therefore you have a wide range of conductivities that might cause a very gradual transitional characteristic that would last for a very long time. So I think that information, that signature, the shape, gives you some very important clues about the geometry, the physics of the system. All right? Matrix compaction and stress sensitivity. They're both the same phenomenon. They're all about the compressibility of the rock and its companion natural fractures. In some cases, this signature right here, where it gets better, where it moves shallower, energy is being added to the system because of the compaction of the rock. Well, specifically the diatomite in the southwestern San Joaquin Valley in California. It has exactly this signature. The diatomite collapses. It's very stress sensitive, but because it is so stress sensitive, as it collapses, it actually adds energy to the system. So it supports the pressure. It actually, the volume, the change of the rock, the physical change of the rock system. That happens in several different Middle Eastern reservoirs. So this is not an uncommon signature. But in the mathematics, that signature occurs because of the violation of the material balance. The reservoir volume is changing because of the collapse. By contrast, many reservoirs, Abo is a really good example of it, the reservoir itself is extremely stress sensitive, and as the pressure difference gets worse and worse and worse, the reservoir actually collapses, but it doesn't collapse in that energy. The loss of permeability outruns, and so the reservoir actually becomes worse, and so the KH drops. All right, so there are several different scenarios that you will see. Most all of them are driven by an understanding of the geology of the system. Aquifers. If you work in Texas, and especially if you work in Houston, which unfortunately is very likely, you will find that every reservoir in the state of Texas is a water drive reservoir. Baloney. That is such nonsense. They have used this explanation of water drive reservoirs as an excuse to mismanage the reservoir. I wound up, I have the privilege of having received an SPE award for my work on water drive reservoirs. I would say that not 1 in 50 of the Texas reservoirs are actually water drive reservoirs. They are misinterpreted because the operators don't care to take care of the water properly. I know, I just committed heresy again. That's okay. When you look at the production histories in this setting, the aquifers will exhibit a variety of different signatures, okay? If I have an active aquifer with no activation pressure, have you done enough work now to know when somebody talks about the threshold entry pressure, that idea clicks? Basically, threshold entry, you've got a chunk of rock, it's got gas in it, you're going to inject water into it. It takes a certain amount of pressure against it to start the water to move into the rock. That's the threshold entry pressure. Once the water starts into the rock, capillary pressure takes over and will pull it through, imbibe it, okay? Well, in many aquifers, they don't have an activation or threshold entry pressure, and the degree of pressure support from the aquifer moving in will create this fold over. This signature right here, by way of anecdote, I had the privilege of doing an investigation for the Bolivian and Argentinian government. They've got a reservoir that crosses the border between the two countries. I didn't make myself popular with either government because the problem was the aquifer, the water drive is on the Argentinian side and the oil is on the Bolivian side. And as you might surmise, the Argentinians wanted me to tell them that the oil was on their side and that the water was on the Bolivian side. And I had the misfortune of having to tell them it was the other way around. I got the wrong answer. Darn. Well, this was the signature, and this was how I was able to tell, because the wells close to the border had this pressure support. The wells further away into Bolivia did not. And as a consequence, I was able to show them the actual aquifer that was providing the energy was to the southeast, which unfortunately put it in Argentina, which meant that there was no money to be made from that. Well, that becomes an important idea. If you've got a reservoir that has a high activation pressure, you'll have to pull it down a lot to get the aquifer to start moving. Once it starts moving, then you see the pressure support. So there's this issue of activation pressure or threshold entry pressure, and then the strength of the aquifer determines the slope of that line. How much energy the aquifer has. A really strong aquifer will have a very steep slope. But sometimes you'll actually see the slope break over and go flat because you've expended the energy. And where's that? In the Marcellus, there is a reservoir known as the Oriskany. The Oriskany is an overpressured aquifer that has really high salinity. And you see that thing. The Marcellus will come rocking along this line, and all of a sudden it'll break over, and the salinity of the water will just go through the roof. The Marcellus water is about 50,000 parts per million. The Oriskany water is around 250,000 parts per million. So you see this breakover where the Oriskany starts kicking in, supporting the pressure, the salinity goes way up, and after a few months, this line breaks back, starts going flat, the salinity goes down because the ariscony has now been excluded. The pressure source from the ariscony has gone away. Is there any other example? Yeah, Barnett. In the Barnett, the Ellenberger does the same thing. In the Barnett, near Fort Worth, Texas, the Ellenberger basically is an aquifer that provides energy to that system. So you do see this signature. It's not uncommon. If the aquifer is passive, all it's doing is acting as if it were a damage source. We're going to look at water floods in a minute, so I'll kind of pass on this one. Multi-phase fractional flow. I've already told you, I've wrestled with you about the idea that this system, I'm going to use a single-phase model as if it were a multi-phase system by virtue of taking into account the mass weight of all the phases. If you leave one out, if you leave one out, you'll see a change in the permeability. Think about that a second. If the water, the oil, and the gas are the consumers of energy in the system, then to leave one of them out imputes that the oil and the gas are now the primary or only consumers of energy. Therefore, I am no longer accounting for all of the energy consumption, so it would be as if the permeability changed. And you see that when you do the calculation. So you do it with all of the phases, then you leave one of them out, you will see the permeability appear to decrease. That reduction in permeability is actually the rel perm. It's actually a measure of the relative permeability of the system. That's kind of cool, because I now have, granted it's not highly rigorous, but it has actually a very good predictor of the change from absolute permeability to rel perm. Okay, now let's think about that in one more step. Suppose the water that's being produced did not come from, is not part of the energy consumption of that system. What would it do? The slope wouldn't change, would it? Because that slope is a measure of the energy being consumed. And if one of the components is not part of the energy consumption of the system, the slope wouldn't change. And that's true of both gas and water, well, and oil, rarely, but once in a while. So, if when you leave out the water phase, you see a slope change, you can be pretty confident that the water is coming from the same zone that the oil and gas are. You leave the water out and the slope does not change, you probably have a bad cement job. Is that simple? Okay. Noise. When the well goes from bubble flow to flow by slugs to mist flow, or vice versa, whatever the combination of phases are, basically you're going to see a change in noise, because this signature, all this noise, is the flow by heads, the sludge flow. And Coleman has a really good article about it. Any of the stuff that Brown and Brill and sorry, what have you ever written, really apply to this. Time-dependent skin. You've heard me just carry on at great length about that. I would encourage you, Marie and Cox just have a really great paper to deal with this idea. Some of the things that are causes of it. Short list. Maybe one of the most surprising ones is that last one. We have historically believed that proppants do not change other than due to crushing or embedment. That's not right. Back in the day when I was at Mines, we had to take our students on summer field trips, and one year we went to Brawley, California. Brawley, California is down to the south end of the Salton Sea, is about 50 feet below sea level. About 10 miles away from Brawley, which is why we went there is a geothermal project producing extremely hot waters out of the rocks below the Salton Sea. One of their worst operational problems is diagenesis. The water that they produce to run the turbines actually has around 200,000 parts per million dissolved solids. On the face of it, that's not a big deal. 200,000 parts. That means that on a mass basis, 1/5 of the weight of the stuff they produce is dissolved stuff. Okay? The surprise is what the stuff is. The 200,000 parts per million of stuff is silicon dioxide. They have to go around the plant about every 6 hours to knock off the stalactites of silicon. What is silicon dioxide? Do you have any silicon dioxide in the room? It's called glass. Glass is silicon dioxide. 1/5 of the mass that they produce from these wells is dissolved glass from the quartz in the rock in the reservoir. Think about that. I mean, it just blew my mind, because here we were walking around. We walked around the plant. In this one place, they had a leak in a pipe, and they'd gone around and they knocked the stalactite of glass off. And when we came back about 30 minutes later, that stupid thing had grown back to about 3 inches long. Glass. Well, that really got me to thinking. And the guys at Baker Hughes have done some really neat work looking at the diagenesis of proppants. A proppant bed that is not correctly chosen for the temperatures and pressures of chemistry can literally be dissolved in a couple of days. Embedment and crushing having nothing to do with it whatsoever. Literally, the water can dissolve the proppant. Whoa. I had that concept I could not grasp it, except having seen what happened there at Raleigh, that this water that they were producing was 1/5 glass, dissolved in the water. I was, incomprehensible almost, but there it was. So, here's this long list, collapse, well, we're stressed, I don't know, all the usual stuff. But the one that may actually be more important than all of the others is that the rock itself is dissolving. Dang. Okay. Time-dependent skin. Well, let's not dwell on that too much, because we want to go look at real data. You've got the notes. Fluids management. I've already carried on at great length about the pressure question. The other big issue in our business, I think, is our failure to manage the liquids, both oil and water, and both oil and gas wells. We had a nice discussion last night, guys. Thank you for coming. We had a really nice discussion last night about the effectiveness of gas lift, the effectiveness of jet pumps, the effectiveness of sucker rod pumps, and the effectiveness of plungers. And now several of you know about my prejudices with regards to plunger lift. And I'm not an advocate of plunger lift, by the way, just so the rest of you know. But the issue is this. If we're doing a good job of removing the liquids from the wellbore, we are also doing a good job of preserving the wellbore. And that, to me, is one of the really key pieces of this story. If we are not removing the liquids efficiently, then shut-ins will always be damaging because of their impact on the rock, the fact that dissimilar waters can fall back into the reservoir and react chemically and react with changes in well perm, cap pressure, etc. Okay? Same business. A very good friend of mine, has the good fortune of having been able to retire because of some of this work. Jim was able to go out in the eastern Niobrara, the shallow Niobrara in eastern Colorado. The pumpers had always told him, these wells don't produce any water. And they were right. They did not produce water to surface. But Jim kept wrestling with, well, how come as they age, they appear to get poorer and poorer and poorer? Finally, he convinced the pumper to shoot some fluid levels, found out that there was standing water in these wells. They didn't produce water to the surface, but the gas, because it's 100% humidity in the reservoir, when the gas would come to the wellbore, it would carry with it water. The water in those wells was drinkable. It was that fresh, all right? Well, here's this water standing in the wellbore. He convinced them to install sucker rod pumps. The installation of sucker rod pumps, the condition was that they would always install the sucker rod pump with the inlet to the pump below the perforations in the rapier. Well, the field super was just panicked about that because you don't do that. Oh, okay, but Jim says, that's what I want you to do. Well, what the field super did, on about 2/3 of the wells, he did it like everybody told him to. But he was honestly a coward. So on the other 1/3 of the wells, he landed the sucker rod pump about 2 joints above the top of the perfs, because he knew that was what was safe and that's what everybody else had done. After we did the investigation of well performance before to after, in the after data, here was this group of wells that had both a change in KH, the reservoir conductivity appeared to improve, and the skin, or apparent fracturing, improved. Major improvements in both, actually. Happened to be about 2/3 of the wells. Made us very suspicious, so we looked at the other population, roughly 1/3. Of that 1/3, they virtually didn't change at all. There was no change in their performance at all. And when we looked at it, that population of wells that didn't change, every one of them were the wells that the field super had instructed the operator to not land the tubing, land pump below the purse. When the sucker rod pump was landed above the purse, no benefit occurred. When it was landed below the purse, which is contrary to what everybody says, but when it was landed below the purse so that the entire formation face would be kept dry, that was the case where the wells were improved. When the pumper did it like tradition says you do it, nothing good happened. Well, that's really this story right here. When the pumping unit was installed where it should be, below the purse, good things happen. Now, that's it. Well, then how much is good enough? Because, gosh, if I land it in a rat hole, I'm going to pump sand, I'm going to gas lock it. No, you're not. No, you're not. Bottom line is the failure rate of pumps landed in the rat hole is no worse than the failure rate of pumps landed above it. And there's some really good data that was taken by the Rocky Mountain Oilfield Technology Center up in Casper that support that observation. I guarantee you, I absolutely guarantee you, if you go into the operations side of our business, you will find people that just get adamant, I mean, just in your face. We're not going to land the pump low, like you said, because we're going to ruin it. Fine, Fred, do what you got to do, but by the way, I have the authority to tell you what to do, and this is how you're going to do it. And they'll be mad at you until they get their bonus check because they did something right. Okay, a proper signature in coal bed methane. Several of you have asked me questions about coal bed methane. This could be a whole 2-week discussion in its own way, but let me cut to the chase. We've already talked about it, so this is really a review question. What is the most energy-consuming phase in a well's behavior? Let me ask it differently. What is the most dense phase in the performance of a well's behavior? Water. Yeah, water. The behavior of a coal bed methane well is not about the gas. It's about the water. And these operators who get all hung up on Lanier coefficients and adsorption and desorption and absorption and what else, they're missing the point because it's about the behavior of the water. If you look at the gas signature, which is typically this S-curve thingy, you've got to have this threshold pressure below which the gas starts to produce, and it's called absorption pressure. Fine, you call it whatever you please. The bottom line is if I include the mass rate of the water and the gas, I will discover that the behavior of the system looks just like every other well in the world. The KHs match the whole bit. So, it really is about looking at how the water works. It is not about looking at the gas phase, because the gas phase at early time represents almost nothing in terms of energy consumption in the system. It's not the primary phase that's affecting the behavior. It's the water. So, it really becomes an important idea. Let's look at the water signature, which is the same physics as the rest of the system. So what we'll see in a coal bed methane system this way, if I look at the behavior just at the gas, I'll see this hump, okay? Because of that hit right there. 1 over Q, so the hump is actually a consequence of the gas rate going down. But if I include the water, I will see that the behavior of the system is this. There's another big issue, and I'm sure, well, I know from the question that was posed, there is the belief that coal bed methane systems exhibit what's called dilatation. Dilatation is the process in diffusion. If you go look at the math that describes Fick's law, in diffusion processes, the permeability has to increase as the desorption occurs. Because there's mass transfer, so the stuff removes itself from the rock has to become more permeable. I have never seen that. I have never once seen that. What you see is as the cleats open, as the natural fractures open, because you've removed the water from them, the reservoir gets better and better and better, not because the reservoir is changing properties, but because the natural fractures are. So that really becomes a key idea in the behavior of a coal bed methane well. If you look at the water plus the gas, the sum of the two tell you how to change the performance of the well by changing the way the cleats work. Okay? Linear systems. A good horizontal will always exhibit linear flow. Why? Well, stop and think about it. Our knowledge base has been based on looking at approximately vertical wells, single point sources penetrating our pipe head. Okay? Now we're drilling very long laterals. The presence of the lateral itself creates an anisotropic system. Okay? So a vertical well basically is that classic point source solution. So it's really easy to think about. But all of a sudden, I've got this very long, and 23,000 foot is the worst case. Not that it's a smart case, but there it was. I've got this really long lateral sitting here producing from this reservoir system. So I have just now created, by virtue of the way I chose to do this business, I have created an anisotropic system. And very commonly, I would say way over 4 out of 5 times, the good laterals will exhibit linear flow in their life. A bad lateral, and honestly, a bad lateral is always going to go into radial flow. That has been my observation. So, the problem is this. When I look at this delta P over QO thingy against log of time, I will see the curve, the signature will do this. It will always do that. When I replot it in the square root of time, it will almost always generate a slope at least approximately a half slope. Square root of time is that theoretical solution for linear flow. So this really gives me some important clues. In one geometry, I see the anisotropy of the system. In the other geometry, I see the anisotropy, but it looks like linear flow. So this tells me that I can give me an estimate, I can get